In this video, I'm going to show you how to do a number of examples of maximum and minimum questions, so to do with applications of the calculus. Many of these questions you can do using other techniques, so if they're involving quadratics, then you can solve them fairly straightforwardly with quadratics, or you can look at a graphical approach, but sometimes you might be specifically asked to use calculus. So I'll show you how to do that, and we'll see how we go. So the first example, it's pretty straightforward. We've got a loop of a string of length 100 centimeters. We want to form it into a rectangle, and then find the maximum area of this rectangle. Okay, so good idea is always to draw a diagram first. Oops, not like that. This. Okay, and we need to designate some variables. So if we just call it x and y. All right, we know that the perimeter equals 100, or has to equal 100, because that's the length of string that we've got, and we know that that's going to be 2 outside x plus y. So then we can say that 50 equals x plus y. Over here we want to talk about the maximum area. So we've got area equals x times y. Now if we rearrange this to get y is 50 minus x, then we can plug that in over here. And we have x times y, which is 50 minus x, which gives us 50x minus x squared. Now this should look familiar from the work we did with quadratics back earlier in the year, but we can solve this one with calculus as well as with our sort of graphical approach that we did last time. So what we're trying to do is maximize the area. So this is our area function, and we want to find the maximum. Obviously the maximum is going to be a turning point or a stationary point. So we can find that location using derivatives and then set it to 0. So if we differentiate the area with respect to x, okay, that gives us 50 minus 2x. Now at a stationary point that's going to be 0, which means that x is 25. Okay, so if the perimeter is 100 and x is 25, y will also be 25, so we've actually got it as a square, which makes sense, because when you have these questions, the maximum area is generally a square, unless you've got some other restriction on it. Okay, and the actual area itself will be 625 centimeters square. Okay, so fairly straightforward, didn't have to graph anything. It was easy to find that maximum point using calculus rather than looking at a graphical solution. Okay, example 2. This is a fairly common kind of question that you get where we have a sheet of metal and we need to fold it into a box so that the area of the metal is set, but this dimension can change. Okay, so this one has side length of 2 meters, which means that whole side is 2 meters and that side is 2 meters. And the metal is going to be folded along the dashed lines to form an open box with a height of x. So if you imagine when you fold these sides up, that's x and that's x. So you've had a little square removed out of each of those sides. Okay, which means that the internal dimensions there is going to be 2 minus 2x. 2 meters minus x minus x. Okay, so we want to show that the volume is given by that. Obviously to do volume we want area of the base times the height. So the area of the base is just going to be 2 minus 2x squared. Okay, if you work that out, you get 4 minus 8x plus 4x squared. And therefore the volume will just be that multiplied by x, because the x is the height. So 4x minus 8x squared plus 4x cubed, which is what we had up here. So we've showed that. Okay, part B says find the value of x that gives this box the maximum volume and show that it's maximum. Okay, so in terms of doing this, you could do it graphically, but that doesn't really show it, unless you sketch a graph, but that's what part C asks you to do. So what we really need to do is find where is the maximum, so where is the stationary point, and then demonstrate that the gradient on either side make that the maximum point rather than a minimum. Okay, so let's differentiate first. Volume with respect to x, which gives us 4 take 16x plus 12x squared. Put that equals 0. And then solve for x, and what you get is 1 or a third. Now, at first glance, both of those seem reasonable. They're not negative, which is good. We can't have a negative x value. However, which one is it? Because it can only be one. Well, in this case, it can only be one. Because if you look at x equals 1, if this value here is 1, then that's going to take that right to here. And it means that you'll have nothing left in terms of the metal. So that doesn't make sense because that's half of this 2 meters here. So we can't have that one. So it must be that x is a third. Okay, now we want to show that the volume is a maximum for that value. Alright, so what we're going to do is our little table, like we were doing in the previous video. I'm just going to flick over. Okay, where we set up our x value and we look at what is the gradient. Is it sloping up, sloping down, positive or negative? Okay. We know that at a third, when x is a third, the gradient is 0. So it's flat. Okay, so what I want to look at is maybe, let's say, 0, something to the left of that. And we want something to the right, but not past 1, because that's our other stationary point. So maybe we'll use a half. Alright, and if you work those out, so obviously if you put 0 into our function here, you get 4, which is positive. So that means it's sloping up. And when you put a half in, you end up with negative 7 on 2. Okay, so we're putting a half into this function here, and it becomes negative. So you get a slope down. Alright, so if you've got a stationary point and the approach from the left is positive and the approach, or the departure from the right is negative, then it's obviously a maximum point. So maximum at x equals 1/3. Okay, now this question says sketch the graph. I'm just going to do it on the class pad to demonstrate. If you had to do it in an exam, then you'd need to label all the relevant points, and I'll talk about that in a sec. Okay, so we're sketching a graph of the volume, okay, not the derivative function, but the volume itself. So we want 4x cubed, take 8x squared, is it plus 4x? Okay, and if we drag that down into our graph window, now I've already adjusted the window so I can see what's going on here. So clearly for x less than 0 doesn't make any sense, so this is really all that the only section of the graph that we're actually interested in is between 0 and 1. Okay, so you can see it's 0 here, this is your maximum, so that's the point we were talking about, maximum of a third, and then coming down here. So if you were sketching this, you'd want to label your intercepts and your maximum point at the very least. Okay, and probably only sketch it over that domain, because outside that domain doesn't make any sense. Okay, the last one says find the values of, or values rather, of x for which the volume is 0.5 meters cubed. Okay, so this one's easy to do on your calculator. Clearly you can do it by hand if you plug that in there and then solve it, but I'll do it graphically because I quite like the way you can see what's going on. So we're doing a g-solve. We want to find the x-calc, okay, when y equals 0.5. Right, so the first one we get here is 0.19. That's okay. We should be able to see that as we go over here, there's going to be another one. So we look at that, and we get 0.5 as well. So 0.19 and 0.5. So x is 0.19 or 0.5 in meters. Okay, and that finishes off that question for you. Okay, this one starts talking about absolute maximums and absolute minimums. So what this refers to is if you've drawn a function over a particular domain, say something like this, okay? Now we would talk about these 2 points, the stationary points on here, being local maximums and minimums. So that's your local maximum, that's your local minimum for your turning points. But over that domain, this is your absolute minimum. It's the smallest value that the function takes over that domain, and this is your absolute maximum. Okay, so basically what you're looking for is what is the smallest value over the defined domain and what is the largest value, and it's not necessarily at the stationary points. So if you find your stationary points, you probably want to check your endpoints as well to make sure that you actually capture that. Also, just pay attention to the function that you're sketching. So what we've got is an fx is x squared plus 2, and from our knowledge of parabolas, that just looks like this. Okay, but we know it's restricted from -2, which might be about here, to 4, which is going to be somewhere up here. Okay, it's going to be symmetrical around the y-axis, so clearly this point is going to be higher than this point because it's further over. So that's 4, that's -2. And we find an absolute maximum and absolute minimum. Clearly the minimum comes down to here. So absolute minimum, and that's just your y-intercept at 0, 2. And the absolute maximum is obviously going to be this one. Okay, so absolute max, and that will be when x is 4. If you plug 4 into there, you just get 18. So really no calculus required for that whatsoever, just a little bit of common sense and some substitution. Okay, but if you did have a function that was a little bit more complicated, then you'd look at finding the local minimums and maximums and then checking your endpoints there. Okay, last question goes back to example 2 with that box. Okay, and what it says is we found the maximum value for the function, but now we're putting a restriction on it and saying, well, x has to be less than or equal to 0.3. Of course, we had x was a third, which is 0.33. Okay, so greater than that. So if we restrict it to x is less than or equal to 0.3, go back to our function. So that was up here somewhere. So if we restrict it to the x value being here, then clearly the volume is going to be less. So all we're doing is finding, well, what is the volume when x equals 0.3? So gsolve again, doing a y calc this time. The x value is 0.3. Okay, and you can see the y value is 0.588. So what if x equals 0.3 meters? The y value, which is your volume, is 0.588 meters cubed. Okay, so if for some manufacturing reason you end up with a maximum dimension for x of being 0.3, then this is the maximum volume that you can have. Okay, so quick summary. The absolute maximum of a function is the maximum value over a defined domain, so that's the key there. It'll change depending on what the domain is. Absolute minimum, same thing, but we're looking at minimum values. The stationary points may not be, in fact often they won't be the absolute maximum or minimum, but we refer to them as local maximum minimums, okay, if they're turning points. So that's for turning points, not so much for, or not the case for inflection points. Okay, so for turning points. If you are looking for absolute maximums and minimums, then always check the endpoints of the given domain and have an idea of what the sketch looks like. Okay, even if you don't want to put it on your calculator, most of the questions you'll get will be sort of polynomials of the second or third degree. So if we're talking quadratics or cubics, you should have a fairly good understanding of what they're going to look like, at least in the basic sense. So you should know whereabouts or at least have some idea of whereabouts your absolute maximums and minimums are coming from. If all else fails, graph it on your calculator.